Kirchhoff problems can be a little cumbersome and easy to make little mistakes on. Let's do WebAssign Kirchhoff number 1. So, what does it consist of? It consists of a circuit that has a battery of 5 volts here. And on this branch, there's a 22 ohm resistor. And then there's a middle branch that has a 56 ohm resistor. And then there's a branch down here that has B1. B1, isn't that nice? B1 in it. And it has a 75 ohm resistor in that branch. Okay. And then these are all connected like this. There's a picture. Now, I'm going to go ahead and label this plus and minus, because these plus and minuses are pretty important. And we need to find the currents in each of the branches. And so we have 3 unknowns. Now, we can pick whichever direction we assume the current is flowing. I'm going to do it like this. Because of the way the battery is positioned, I'm going to assume that current in this branch is flowing like this. And this is, I'm going to call I1. Down here, because the battery is positioned like you see, I'm going to assume the current's flowing like this. I'm going to call this I3. Now, with that assumption in mind, that means the current here is also I3, and the current this way, I mean, if the current's flowing through here, it only has one way to go. This is I1, this is I3, and so Kirchhoff's point rule tells us something about what has to happen here. Namely, I1 has to go in. Okay, I1, if it's flowing here, it can't go this way. It can't go in this direction because I3 is going up. So the only choice it has is to flow this way, which is I2, which is I1 plus I3. There you go. Now that's a nice setup. And the reason what I did was so important, because we used the point rule to eliminate one of the variables, namely I2. We don't have to worry about I2 now. Now we have 2 unknowns, I1 and I3. I1, I3, I3. So that'll make it a little simpler. So now, we have some other choices. We've got 3 loops. We got the top loop, the bottom loop, and the whole external loop. And we can choose which of those 2 we use to get 2 equations to solve for the unknowns. And we can choose what direction we analyze it in as well. So what I'm going to do is the following. I kind of have a bias toward clockwise. So I'm going to go clockwise around here. I'm going to call this equation 1. And I'm going to go clockwise here as well and call this equation 2. You can go counterclockwise. You can use the outer loop in one of these. There's different things you can do. If we have 20 people solving this problem, our equations will probably have 20 variations because no one will choose everything exactly the same. But as long as you're consistent, everything works out great. And that's our goal, of course. So let's then now write the equation for first loop equation and second loop equation. So in the first one, I've already chosen my direction of analysis, which is clockwise. Now you can pick anywhere you want. I like to pick before the battery in a circuit, if there is a battery. So that's kind of like picking here. All right, I'm going to start here. I'm going to go clockwise. When we go clockwise around here, we notice it goes from plus to minus. If you go from plus to minus, it's a drop. If you go from minus to plus, it's a rise. Having said that, and this is so easy to make mistakes with, let's draw the plus and minuses on the resistors based on the direction of current that we've chosen. Since the current's flowing this way, I1, that means it's plus here and minus here. Down on the second one, the current's flowing to the right, that means it's plus here and minus here. This one, current's flowing to the left, that means it's plus here and minus here. Now if we're wrong about our assumed direction of currents, Our answer for the current will be negative, and it's as simple as that. But we just maintain consistency throughout the whole problem. So loop number one. Loop number one, I'm starting here. I'm going to hit the battery, and it's a drop of 5. So I say minus 5. And then we have a rise across this resistor. So it's going to be plus 22, and the current is I1. And that's the voltage across this one, or the voltage drop. We continue on here, and we have a rise, because we're going against the current, of 56I1. And we also have a rise of 56I3. Both of those are in there. So that is equal to 0. So there's our first equation. Second equation, I'm going to use this one. Now, I could start here again, but heck, I'm going to start right here, because I like to start on the front side of the battery, whichever way I'm going. So it's going to be a rise of B1. Now, I could write B1, or I could use an example, student example. Voltage there is 4.36. Yours will be something else, but there it is. 4.36. Then we come around here, and we notice we're going in this direction. It's a drop. It's a drop of 56 I1, and also a drop of 56 I3. Notice on this second loop, we're analyzing it the other way, so its voltage drops. In the first loop, we analyzed this, we were going to the left, it was a rise of those two. That's just how it works, and it's so important. Any one sign problem that you have will screw your entire problem up. So that's just the way it is. So we've come all the way around here. Now we have one more resistor, and it's a drop, so it's minus 75 I3 is equal to 0. We've done a lot of the work. We got the equations written correctly, and so now at least we have a chance to make these things work right. So now we got to bring things, let's simplify. Equation 1. So what I'm going to do is rewrite this, minus 5 plus 78 I1, these two, plus 56 I3 is equal to 0. Equation 2 simplified, 4.36 minus 56 I1, and then we have minus 56 and minus 75, minus 131 I3 is equal to 0. There we go. They're now simplified. Now what we have to do is eliminate either I1 or I3. So we got to perform a math operation on this. So when we add these together, one of them goes away. I want to solve for I1, so I'm going to eliminate I3. To eliminate I3, we need a common factor. Well, these numbers aren't pretty. So I'm going to, if I multiply this by 56, I'm sorry, this 56 by 131, if I multiply the 131 by 56, these will both be the same. And then this is plus, this is minus already, so we can add them and they'll go away. So I'm going to multiply this by 131 on this equation. Yeah, pencil's giving me trouble. On this one, I'm going to multiply it by 56. All right, and that, by doing that, it'll make I3 go away, as I'm repeating myself now. So let's go ahead and do that. So I'm going to rewrite the equations again. Yes, you have to do this. There's no shortcut. When I multiply this by 131, I'm going to get minus 655 plus 10,218 I1. Yeah, kind of a pain. And then I'm going to get plus 7336 I3 is equal to 0. Now when I multiply this whole thing by 56, I'm going to get 244 minus 3136 I1 minus 7336 I3 is equal to 0. Notice, that was my goal, is to make these two factors the same. So now when we add them together, I get minus 411 plus 7082 I1 plus 0 equals 0. There it is. And Now, we've done most of the work in this problem. We can say, therefore, I1 equals, okay, if I bring this over to this side, 411 over 7082 is equal to 0.058, which is 58 milliamps. And since it's positive, it means our assumed direction of current is correct. It's to the left. Now, I3. What's I3? Well, I'm going to take this, and I'm going to stick that value of I1 into one of my equations. I'll go ahead and choose this one just because I feel like it. I could plug it into here. All right. And so we're going to sub that in, bring it down here, and then what we have is, okay, 244 minus 3136 I1. I'm going to be careful. What I'm going to do is convert that to amps. Okay, just to make sure that we don't have any issues. So that's 0.058. 0.058 amps. Minus 7336 I3 is equal to 0. There's our equation to solve. You notice all it has in it. Let's focus this here. The only thing it has in it is I3 as a variable. So we can bring this over to this side, and then, all right, so I'm going to go ahead and just solve in one line here, I3. Therefore, I3 is equal to 244 minus, when you multiply this together, you get 182 all over 7336, and that gives us 8.5 milliamps. Okay, it's 0.008 amps. Now, it's positive again. Therefore, our assumed direction of I3 was correct, and it's in that direction. Then finally, I2 is equal to I1 plus I3, which is 58 milliamps, plus 8.5 milliamps, which is 66.5 milliamps. And we have solved our problem. Since this again is positive, it means our assumed direction of I2 is correct. It's to the right. If any of these were negative, they'd be in the other direction. So there is 13 minutes of solution time for this problem. There's no real shortcuts. You got to take the time to do it. That was fun. Thank you very much.